So I'm glad to greet you on the final epic review lecture in all our course. Here we will review all the things we learned in these 2 semesters, and I will show you a few results of our small group which we had done during this year. So first of all, we are working in the field of computational material design. And you saw very clearly how we got from structure to the properties. So we started in each our calculations, we started from the structure, then we calculated energy, then we calculated band structure, dose, and some other properties. In computational material design, there is another step. This is very crucial step, but here's another step. So how to get structure? Usually we go to materials project, the database, and then took the structure from materials project. But that's not the only way. So materials project also had to be filled by some way. And somehow there are a few methods how to get the structure. So the most important is experiment. We have the crystal, we made some X-ray diffraction or lead diffraction or some other things, experimental things, and then we got the structure, or we can predict it somehow from our maybe chemical intuition, from our previous knowledge. And in June, it will be defense of master studies of Bogdan, which with him we are working together, and he will show how to do it with genetic algorithms, how to get structure from the scratch, from knowing the names of atoms and some other few parameters. What's the okay? How to get from here to here? We should solve Schrödinger equation. Two types of Schrödinger equation: time dependent, it's crazy, and stationary. So we worked with stationary Schrödinger equation, and here is Hamiltonian, here is some eigenvalue, what is energy of our system, and psi function. And for many electrons, for n electrons, this equation it is too hard to solve. So we have this n dependency. So our psi function depends on n parameters, and n can be like Avogadro number, 10 in the power 23, and it's really possible to deal with Schrödinger equation analytically. So we can't solve it analytically for more than 2 parameters. So maybe we should do something numerically. Numerically, we can make some pre-calculation simplifications. So one of the simplifications, Born-Oppenheimer. Can somebody tell me the idea of Born-Oppenheimer approximation? So what was the idea? Why do we need them?
We treat the atomic nuclei as basically stationary, and electrons just exist in the field created, but they don't interact with each other. So
yes. So you're right. So we need Born-Oppenheimer approximation just to discard this ionic part. We can take this Schrödinger equation. So here is Hamiltonian. It consists of kinetic energy of nuclei, kinetic energy of electrons, electrons interactions, nuclei interaction, electron nuclei interaction. So, and we can discard this and this, and we can simplify our psi function. So we can say that these nuclei, they're too huge, they're too big, and then we just remove this from our equation. We get only these electrons and some external field, as you have said. So some external field of this nuclei. So that's the idea, and it's very useful because we really make our system simpler. Then we can make another thing. So another step in our simplification. Its step was done by Hartree, and then it was improved by Vladimir Fock. So we took this complex psi function with a lot of connections, and we told that this psi function, it consists of independent small psi functions of each electron, which don't connect. So they don't connect, but they feel each other. So one electron, it is one electron in the field, in the mean field of all other electrons. So this our self-consistent calculations, mean field calculations. So they have in the basics this idea that we have one electron system. It's only one electron system, but we have a lot of electrons. Yeah, and we should solve just a system of these equations, psi alpha e. So and in these equations now we can obtain very important term which calls Hartree term. So it's interactions is just Coulomb interactions between electron and the field of other electrons. So this Hartree term. What have done Vladimir Fock? So it was Hartree method. Now it's Hartree-Fock method. He included. So he expanded this method to include fermions. Because what's different between fermions and bosons? When we have constrain when we construct a psi function for fermions, and then we change their places. So we should change the sign. That's some definition of fermions. It's antisymmetrical wave function. And when we include this, so we can include it by Slater determinant. When we it's just from definition from determinant. When we take this column and we exchange them, it will the sign will be changed on opposite. So when we take this Slater determinant, not this psi functions like just they are orthogonal. That's why we can just multiply them, but slightly more complex system with Slater determinant, we get such interesting things like these two integrals, as Coulomb integral and exchange integral. This is just this is just a Hamiltonian for one electron system and nothing special here. But these integrals, Coulomb integral and exchange integral, they are very interesting. What's the difference between them? So here I see that here's one electron, psi complex conjugated E, and here is the same psi functions, but for another electron in another position, x2. Yeah, but then we exchange them. That's why it's called exchange integral. So I took one complex conjugated from right part and moved it on the left part. So I have now one psi function psi e and then psi g in left part, and the same but complex conjugated in the right part. It's called exchange integral. And it looks like that nothing should happen, but a lot of things happens, because by this operation we include spins. So it's quantum effect. There is no such effect when we use only classical system, because in classical systems there are no psi functions, there are no Slater determinants. We just take the formula from ninth grade in this school. And this exchange integral, it arises from Hartree-Fock method, and it will be very important then. So you already know how it's important. Another useful model was Thomas-Fermi model. Proposed in 1930s or in the late 1920s, I don't remember exactly. So the idea was to approximate our crystal structure by electron gas. So we take we say that electron behaves as electron gas, which exists in some potential VR, which asymptotically approaches zero at when R goes to infinity. So in this approximation, we take some state. We say that in the state there are two electrons. the state size is h divided by L. H is Planck constant. We take it from uncertainty principle. So and we divide all the space with the states. Then we calculate the biggest energy of electron. If then we say that all the states are filled by electrons, and it is filled with the same density. So it means that if we will take some circle around the dot r, around point r, coordinate r, so the number of electrons is fixed there. That's why it is also called local density approximation, because we say that local density is constant. And then this model, it became some ground for first models of Kohn-Sham equations, for Kohn-Sham potentials. So, but it arose from 100 years old work by Thomas and Fermi. And this approach, we take this kinetic energy, we say that it is approximately equals to this local density approximated kinetic energy. Then we move to single electron because we don't know how to work with a lot of electrons. We know how to work with single electron. Then we make some calculations and we got this this formula for kinetic energy, this LDA for single electron. All other part of Tn we don't know. Then it will be called correlation energy. So we know the single electron energy, but we don't know the rest. And we say that it's some unknown mystical correlated energy. Then we have Hartree energy. So potential energy we approximate by Hartree energy. It's just canonical interaction between some electron and all other electrons. But we also make these approximations and we don't know the rest from the real potential. And we call it exchange energy. So this exchange energy, it arises from that quantum properties, which I described before. So they was shown by Hartree and Fock, mostly by Fock, I think. And then we say that it's some property which created by spins, because electrons in the atom, they tend to avoid each other if they have the same spin, and they also tend to avoid each other because they have the same electronic charge. So same spins avoid each other, same electrons avoid each other, and we don't know the resulting position, how they arrange. This is exchange energy. And in total, we have the total energy of the system. And one very important thing, another important thing, all the things are important, that it depends only on n, on electronic density. So it's like c squared, and we can build this theoretically. We can build this distribution of electrons, and now it depends not on crazy number of parameters, but only on 3 parameters, excluding that. That was so it's like some historical review. So we took this simplification, Born-Oppenheimer. Then it was simplification by Hartree. He divided this huge psi function. Then it was some improvement by Fock. He included fermions. And then it was another model, but it is also very important, and it based on Hartree-Fock method because it uses this Hartree energy. But it depends on n, so it is another level of simplification. Then we can create even more simplification. So it calls density functional theory. So it's based on Hohenberg-Kohn theorems and on Kohn-Sham equation. So Hohenberg-Kohn theorems, they tell us that all properties are determined by the electronic density. If we know electronic density, this distribution of electrons, we know everything. The energy function of the ground state, the lowest energy ground state, is determined by electronic density of the ground state. So if you know electronic density of the lowest energy, that's why we know energy of ground state, and we know it. So we don't have, for example, 2 different energies for the same ground state. So we have only one ground state energy for one ground state electronic density. And Kohn-Sham equations, it's some way to solve it in interactive manner. The idea of Kohn-Sham equations is we take the real system and substitute it by system of non-interactive electrons, Hartree approach, yeah, non-interactive electrons. And then we create this system of equations. So it was like Kohn-Sham and Walter Kohn, 1965. Then Kohn got Nobel Prize. Kohn-Sham didn't got Nobel Prize. Kohn-Sham equations. So three equations. It's a system of three basic equations. One of them is Kohn-Sham potential. It's like some complex potential of some external field of Hartree energy interactions and exchange correlation, that parts which we don't know from kinetic energy, from potential energy. Then we should solve this one single particle small Schrödinger equations with this potential, with this potential. And then we get psi functions, and by these psi functions, we create new electron density. And then we start from now. So from this electron density, we substitute here, and then we make this cycle on and on. And it's important that we create the schema in that way that electronic density of our single particle system is the same as electronic density for non-single particle energy. And this important step arises from Hohenberg-Kohn theorems. So Hohenberg-Kohn theorems tells us that they should be the same, because we don't have two electronic densities of ground state. And the cycle. So a lot of times we have solved this cycle doing our calculations. It's a Kohn-Sham algorithm. So we start from electronic density and first electronic density composed of pseudo-potentials. So we use pseudo-potentials in our calculations. Somehow the problem composes the starting electronic density. It's create electronic density, but we don't have better. Then we create this Sham potential with this electronic density. Solve this Schrödinger equations, substituting here this potential. Then we get psi functions, create new electronic density, and then we check our criteria, our threshold criteria. So if it is satisfied, so the difference between this electronic density and previous electronic density is lower than something. Usually we use 10⁻⁸ for energy, not for electronic density, but for energy. For phonons, we used 10⁻12 or 14 even. If yes, if satisfies, then we can create a lot of things. No, we go on another circle. So this thing was awarded by Nobel Prize to Walter Kohn. Yeah, how in some programs as Quantum Espresso, we can deal with each part of this equation. So for kinetic energy, we have approximations like non-relativistic, we just take Schrödinger equation. Scalar relativistic means that we take Dirac equation with some relativistic electrons. And full relativistic means that we take Dirac equation, but plus spin orbital interactions. So this is we also made the calculations, and you saw how huge they are. So it took even for simple systems like few gigabytes of RAM to make this calculation. Then how we approximate this external potential. So external potential is potential of nuclei from Born-Oppenheimer approximation. We approximated them by pseudo potentials. So we thought that we are interested only in some valence electrons in the outer shell, and we don't care about these electrons close to the core. We call them core electrons. And we approximate these core electrons by some smooth potential, pseudo potential. This smooth potential, it is the same from some distance from the core, it is the same as potential of electrons. It's simplification to make the calculations here. And then Hartree energy is just Hartree energy. Nothing to tell here. And then exchange correlation. This is the most tricky part. we can do it, but it's really hard to do something with exchange correlation. And we have a lot of approximations, local density, GGA, we also made calculation with it. MetaGGA, we still didn't do it. I hope soon our quantum space will be upgraded also to include these calculations for some research. And there is some accuracy stairway for these methods to approximate exchange correlation. The ground here is Hartree-Fock theory. From Hartree-Fock theory, this problem rises. We first knew about this exchange integral from Hartree-Fock theory. Then it goes LDA, Thomas-Fermi model, improved in a lot of times since the time of Fermi and Thomas. It depends only on electronic density. Then we add then we improve this and we add some density gradient. So that's not constant now, but it has some gradient. It differs in some way. So here is gradient. Then we make another improvement, MetaGGA. So I add gradient of kinetic energy density. It's closer to reality. Then we have some hybrid functionals. So they're composed of this, and this to include some long range interactions, because it's a problem. We are working with unit cell, yeah. But some systems, they are bigger, so they have some interactions bigger than unit cell. So for example, if we have some cool interactions in polar materials, so we had to do something. And hybrid materials, hybrid functionals, which include this Hartree-Fock theory, which can be expanded for these problems. So they're really useful, but it's crazy to make some calculations with them. And some non-local methods, fully non-local methods, I almost have no experience with them, so it's not a lot to say about it. Local density approximations, our first level, we made calculations with it. As I have told, it's LDA from Thomas-Fermi, and then exchange energy, and exchange energy functional is also calculated from this electronic gas, and we can make some in general form with spins. There are a lot of functionals. It was really successful. So it was the first LDA. The first LDA which is useful for calculations was proposed by Kohn-Sham in their paper, 1965 paper. But they didn't have enough computer researchers. It was 1965 to make some calculations. Then in 1980s, some computers was available, and then in 1990s, and then it was some boom of this methods. So a lot of this local density approximation methods was made in 1980s when they was really very successful. And in our calculations, we use this Perdue-Zunger method, which is even now each year like 1,000 articles cite this pseudo potential, this method. Gradient approximation. So we have this in LDA, but for GGA we had to add some gradient of this kinetic energy. So we have this kinetic energy single particle. We add some gradient of electronic density. Then we have some exchange energy with LDA, and we also add some part with gradient of electronic density. In general form, it depends on electronic density only its gradient. So it is better. This method is better than LDA. So and we have super successful PBE, Perdue, Burke, Eisenhoff. Functional, GGA functional. So most of our calculations we made with GGA, and you saw that it is stable. So we can it has not huge amount of some mistakes, so it's easy to calculate almost everything with it. It's non-empirical. There are no some parameters which you should take from somewhere. Yeah, that's cited, I think maybe like near 108,000 times by now. Third level, MetaGGA. So we made more improvements to our methods. We had included this GJ part, this gradient, and now we we can include some local terms which cause kinetic energy density, and we should now we have. So you see, we have this electronic density gradient in this second. So it's like it's LDA. This is part of GGA, and this is part of MetaGGA. So we take this kinetic energy density and it's the kinetic energy gradient, and it works almost as fast as GGA, but with better accuracy, and it gives us better results. For example, for band gap. Band gap is some problem. Yeah, scan is one of the most popular functionals, and here you can see that, for example, for some systems, it's some Bari TO3, Plumon TO3, so I think they're rather complex systems. They take LDA in PBE 1.7 electron volts gap. For scan, it is 213. Experimental 338. So it's still not experimental accuracy, but it is better than LDA and PBE at almost their cost. And fourth level, hybrid functionals. So it's like when we take some parts of, so we take some Frankenstein potential, we take some parts of different potentials, and then for each for some problem, we have some problem. We know that, for example, it has this, in this material it will be some non-local interactions, and then we create some exchange potential, hybrid potential, to deal with this problem. What's the idea? So the idea to add some non-local parts. How it is it's made? It's made with such function. So 1 divided by r, and it is split into short range interactions and long range interactions. So for short range interactions, for example, here are some popular hybrid functionals, and we see that HSE 06 for short range, it uses Hartree-Fock. Then it uses also PBE for short range, and for long range for exchange energy for short range. It is Hartree-Fock and PBE. Then for long range, it uses only PBE, not Hartree-Fock. Yeah. So if we are here only in short range, we should get like PBE plus Hartree-Fock. Only in long range, we should use only PBE. Yeah, and that works. So that works in constructing, for example, good. I like this name. So it works in constructing good calculation systems for band gaps. So we can obtain rather good band gaps with these potentials, but they cost a lot of computational power. So here are some. We can make some comparisons. PBE and here LDA blue circles, and these triangles, white triangles, HS here. So, and we see that for here this red line is actual band gaps, and we can see that these triangles, they goes almost to this line, but LDA don't works. It don't work. For example, for diamond, we get like 4 by HSE, but with LDA we get like no, we have like 6 by HSE, which is real, and only 4 less than 4 by LDA. So it's a really huge difference. But of course it costs. If you use LDA or OGA, you should know just the thing that that our band gap will be underestimated. Because all these methods, LDA, it was made for metals. It was good for metals because metals can be normally approximated with these electronic gases, but these materials, they're not metals, they're insulators.
I have one remark to add. As I just saw zinc oxide at this picture.
Yeah.
And I was actually able to almost reproduce the experimental band gap of zinc oxide by artificially tuning the Hubbard parameters of zinc 3D orbitals, but also oxygen 2p orbitals. It was not my idea. I took it from one article where they showed that this specific combination of those numbers makes the best reproduction of the experimental results. And with those parameters applied, I got something like 313 or 314 volts.
Yeah, but it's tricky thing. So yeah, of course we can improve these results by adding some Hubbard parameter on outer orbitals.
But it feels like some sorcery, some wizardry.
Yeah, you should know for this trick. You should know the experimental data. If you don't know experimental data, you don't know at which parameter you should make these calculations. Yeah, of course, by some tricks we can get. For example, here you see with U2. So they took Feia with U2. So they made this cover parameter by U2 to just to improve this results. Okay, that was about density functional theory. So this is which stands behind our calculations. And now, what properties we can calculate? And what properties we have calculated on our seminars? So total ground state energy, just from SCF calculations. Band structure and electronic density of states, they're combined usually. So band structure and electronic density of states, we calculated 1-to-1. Then Fermi surfaces. This we done in the first term, these things. Then we moved to fat bands, means carries over DOS. When we take this density of states on each band, and we create like 3D DOS. Spin polarized electronic properties. So how this band structure will be different for different spin orientation is in magnetic materials. Spin orbital interactions, we also included it for some heavy items, and we saw that split that some band structure, it was slightly splitted because of this complex quantum interaction. Then we also worked with phonons on dispersion DOS. Electron-phonon interactions we got from this some Eliashberg spectral function, and then we got critical sample conduction temperature. That's not all the properties. We also can calculate, for example, work function, which is Mikhailov's work. We can calculate optical properties, some dielectric matrices, a lot of properties, a lot of properties.
You can calculate optical properties.
Yeah, you can calculate dielectric matrix.
Also, yes. I think you can. There are modules to reproduce diffraction spectra and
diffraction, mechanical things like bulk modulus, some Poisson modulus. So not only this. This is some kind of this electronic properties, and that's some kind of dynamical properties, phonon dynamics. So band structure, yeah, we have. If we will start from this chain of atoms, we can say that if they have the same states, it will be just like sum of this exponents with 0 in the power of 0, like just sum of this psi function of each atom. It's total psi function. If we have different, if these atoms in different states, like this is dashed circle and free circle, yeah, it means that it will be like anti-bonding properties. So it's here is psi function, here is minor psi function. So the energy will be dropped. And we can say that, let's say that this same state chain is some kind of minimum of our energy. And when we make it is mixed, it will be a maximum of our energy. So our energy of the system goes from the 0 from the system goes here to the fully mixed states. And here you see that it can be approximated by some parabola like kinetic energy p squared or hk squared. Because it depends on k wave vector, it's easier to work in reciprocal space. And that's why we worked in that brilliant zone. In all calculations was done in brilliant zone because it's easy to make this graph from dependent from this k vector. And you see that for this chain, if you will play with this parameter, with the distance between atom, so even distance is rather huge, we have a rather narrow band. Then we make distance shorter. We have some parabola, small parabola, and even shorter we have this huge parabola. So that's some basic rules. So when atoms are close, this psi function it needs some space. So because we have this uncertainty principle, it will be huger, it will be bigger.
I think for one-dimensional chain of atoms, you can show it analytically, and the solution becomes something like alpha plus 2 beta cosine something, and this beta coefficient actually determines the bits of the band, and it's determined by the distance between atoms.
Yeah. You can, for example, here is now that reference. In Southern Electronic Structure book, these things are very nicely described with these formulas. For surface, for some brilliant zone in surface, we have some simple brilliant zone. It's just square. We have gamma point. Now we have this gamma point, which is center of brilliant zone. And I hope that now you have more knowledge and you have experience in working with these dots, and you know what they mean. So gamma point in the center of brilliant zone, x is some point in the center of some side of this brilliant zone, and m in the corner. Yeah, we have this gamma x m. So three interesting points. All other points are intermediate in them. So we can say that here in gamma point for our simple stuff. So we just like one infinite chain, another infinite chain, and we made this squared surface. So in gamma point we have the lowest energy. Then we moved to x. In x point, what we will have. So in x point, one of this change, one of these lines we change to opposite. That's why we have energy which will be raised, and here we have even more chaos. So we have this mixed states. That's why the energy even bigger here. So we go from gamma to x, then from x to m by these parabolas. So just take the parabolas, and then from m to gamma, and we moved in this path. So we also choose in our seminars, we choose the path for some complex 3D structures like this brilliant zone for cubic crystal, cubic symmetry. So it will be like this. We can calculate this brilliant zone vectors in reciprocal space with these formulas from vectors for the just crystal in for crystal in real space. And then, yeah, and then of course we have some gamma point, we have some X point at the center of this site, then we have some M. I'm not sure that M is here, but maybe it's here. So we have some interesting points. And the density of states, which is tightly connected to band structure. So you can say that if our band is narrow, it means that a lot of states here, and if it rises with some huge angle, so we have lower number of states here. It's like, how to say, it's like resolution. It's like resolution. Here we have a lot of these dots, and here we have lower number of dots. That's why a number of doses will be huge here, and the edges, and here we will have a small number of dots. So it's also parabola. It's also parabola, but rotated 90 degrees. And even with these simple parabolas, we can make rather good approximations. So, for example, this lowest narrow band will create rather huge dose. Here it is the combination of 3 bands and 1 band XY. It is very flat. That's why we have this peak. Then we have this XZ, which is not so flat, but also rather flat. So we have this, and very wide Z squared. We have this dose. Yeah, and we made some kind of calculations. So it's from a previous term obtained by OFC. So it's for graphite. We see this band structure for graphite. And we have calculated dots. We see that in graphite we have this interesting dots at which bands touch each other. So gamma M K gamma. So it's like hexagonal brilliant zone. And then we see the drop of density of states here in this point. And also OFC had made different states, so it showed different states, like total dose, blue and green p states of C of carbon. Yeah, of course, carbon outer shell of carbons 2s and 2p. In p we have only 4 electrons. Yeah, for this, and for p we have a lot of places where electron can be seated. And that's why it makes this p states of carbon gives a lot of states. And s states, they are working here in low energy and working here. This results from Igor's a manuscript about apatite, the LK99, which was some in big news. Yeah, and you can see how complex can be this band structure for a lot of atoms, because this apatite, how many 41 atoms? 41. Yeah, so 41 atoms in the unit cell. We have such crazy band structure, and we see that it is also almost narrowed. Yeah, but it is not super conducting. Yeah. Despite this narrow lines at Fermi level, and we see this crazy density of states, spin polarized density of states, which I think is good, and you have submitted this manuscript, as I know.
Yes, they are still under revision. Also, it was actually put there in this context to demonstrate the limitation of DFT plus U approach in this case, because experimentally all the subsequent synthesis and synthesized materials, they prove to be semiconducting. And actually, there is a gap on the Fermi level. There should be one. But in DFT, it does not appear. And as I speculate in the article, this is due to the nature of the strong correlation of those proper D orbitals that even DFT plus C cannot quite well demonstrate it. And the people were using other more sophisticated methods in theory as well to prove that it's actually.
So you mean that we shouldn't have this DOS on Fermi level?
Yeah, obtains it in DFT, but it's actually more tricky.
And in trials, as we see from Kuprum D and from Green from OP.
Yes, they are strongly hybridized.
So in some way we should remove also OP, but it's not like relativistic. Yeah, but
complicated.
Yeah, but it shows us how beautiful plots we can make using this projected density of states approach with spin polarized. So we have spins. We can spins up and we have spins down, and you see that they are rather different. So this peak shouldn't be there, as we know from experiment. Yeah, but still, it really shows maybe some limitation of. And what you did use? You use U for PB and for Kuprum, or only for Kuprum?
Only for Kuprum.
So Kuprum D here was added by Hubbard correction, because it is some strongly correlated electrons, because Kuprum is huge atom. Then it's the results of Mikhailo for ferrocyan. We have this band structure. We also have corresponding density of states, projected density of states for ferrum SPD, the same for Celian. And also you can see here Fermi surface. So we also have constructed this Fermi surface, and you can see connection between bands and Fermi surface. For example, the Fermi surface shows us the bands which cross Fermi level, and how we can, by our eye, to connect this picture to this picture. For example, we see from gamma to Z in brilliant zone, so it's like some vertical moving from the center to the edge of brilliant zone. From gamma to Z, we have this very narrow band, and this band, it will be this cylinder. In 3D, this band will create cylinder, but we have not only one band, we have like some kind of 3 bands. You see one band and another, and so 3 bands goes to gamma, and then these 3 bands, they goes to Z, and that's why we have 3 cylinders here, one inside other. And this narrow band, it is in the middle. You see, this is some Röntgen of this cylinder. It's in the middle. Yeah, and then it even roses when we approach into Z, and it becomes slightly wider when we approach to Z. And another cylinder, it is in the corner of our brilliant zone. It is created by these bands, which goes from the conductor zone, from the top zone in the M, so it goes under Fermi level at M point, and A point, it corresponds to M, so they are located one above other, and we see that at M point it is rather it is not white. White here you see it is not so white, but at M point it is very white at A point, and it becomes white. So so we can imagine how this band structure goes to create some such complex Fermi surface, right? And to show where these electrons located, their velocities. This also was some student work. But now, few words about phonons. We also made calculations for phonons. Simple phonons model is when we take the same balls, connect them with springs, with J parameter hardness of this spring, and then we can calculate its energy. It will be just kinetic energy of this balls connected with spring. Yeah, but if we are going, yeah, we can get its dispersion, its frequency of this balls, and we will see that it also has some unit cell structure like in Brilliant zone. So we have this gamma point, zero calculations, and at some edges of the gamma of this zone, of this Brilliant zone, we will have some the biggest frequency. Yeah, and when we will go to more complex system, for example, we will take two types of these balls. We will have dispersion with this term, this plus minus term, and minus term, and creates us this bands. They are called acoustic bands. It's like sound dispersion in the sound propagation in the material. And here is optical bands. Why optical? Because they have they have a huge meaning, for example, in Raman spectral calculations. So that's about optical bands. So yeah, about optical properties, we can calculate within the routine pH.x. We can also calculate some Raman spectra. This is how this is how it looks like. So we have at gamma point, we have these acoustic bands when atoms move in the same direction. And when they move in opposite directions, we have these optical bands with a very huge frequency. And the acoustic bands, they always go from the zero from gamma, and then they go somewhere. So if we have some negative modes here, we also got negative modes in our seminars. It means that maybe we don't have enough accuracy, or maybe our system is dynamic unstable, and we should change atoms somehow to make it dynamically stable again. Make this crystal dynamically stable again. Yeah, and that's our results from one of laboratory works. It's magnesium. It's titanium gallium. We have built this phonon dispersion. It was made with enough accuracy because we have this beautiful gamma acoustic bands and no negative frequencies. Yeah, and we have this phonon dose. The meaning is the same as electronic density. So, EDA of this dose of state, phonon density of state, is the same as electronic density of state. We have a lower number of states here in the low frequencies, but we have a lot of states from states in huge frequencies because of this optical bands. Then also we studied electron-phonon interactions. So when it's another step from phonons, and it's our road to superconductivity because this electron interacts with ions. It makes some phonon wave of these ions, and it can interact via this phonon wave with another electron, and this is Barton-Cooper-Schrieffer scheme of superconductivity, like Cooper pairing. And in the point of view of density of states, we will have some gap, which is called superconductive gap. So we will have some near Fermi level, some DOS, we will have this DOS peaks, because a lot of electrons will have the same energy, and that's why they will have a lot of states in the same energy interval, and we will have these peaks. And that's not only one, and that's not 100% for sure. But if you see such peaks near Fermi levels and Fermi level and some small band, maybe we have some superconductivity. Yeah, maybe. Not sure, but maybe. I think that this formula shows the way we made from the very beginning to the end. So we started in this Hamiltonian. So we started from the electrons. I showed it in the beginning of this lecture. Then we have added phonons. So for electrons, we have this operator of annihilation and creation C. For phonons A. And you see that here only C operators, here only A operators, and electron-phonon interactions. They are mixed C and Q of electrons and phonons and some matrix. And our goal of our equations was to get this matrix. So this it's like strength of the coupling between the electrons and the phonon subsystems. So if we know this matrix, we can calculate a lot of properties, and we have done it. So we have this electron-phonon Hamiltonian. Then we have this matrix gamma. From this matrix, we can calculate electronic spectral function. It's biologically, it's also looks like this. Looks like density of states of phonon density of states, because we have this delta functions here. So it just can say it's like density of states of phonon lined winds. We can calculate.
Two particle density of states or something.
Yeah. We can create also this coupling constant, and now in coupling constant, now in spectral function, we can get critical temperature from this Macmillan formula. Yeah, it is rather empirical because we don't know this mu. Mu is some screening constant. So we only know the range. It's like from 0.05 to 0.2 or 15 or 2. So we know only the range. So we have to play with it somehow. And here how we played with it. So it's like the spectral function, also from our one of our laboratory works. So spectral function for different Brownian constants. And spectral and the approximation of TC for magnesium B2. It's for magnesium B2 because it has the biggest this Barney-Cooper-Schrieffer superconductive. So it's not like super huge. It's like 39 kelvins. Yeah, here it is. I don't remember which omega we used, which mu we used from here, but in our lab it was like range from, I don't remember, like from 20 to something. Yes, and this is the biggest, the edge of this approximations, edge in the bigger side. So it was a really huge journey, and I greeting you, all of you. So you made a lot of calculations, a lot of experience. Maybe it will be useful for you, and I see that for some of you it's useful for scientific work, and that's all false. But not all for the homework. And next time it will be like the last seminar of the semester, and we have to make all the models which I sent you for. This is all. I think that all questions which can be asked, you have asked before.
Thank you for the course.
Yeah, thank you for your attending the course.